Swayam Prabha. Digital India. Educated India.
Hello everyone, I once again welcome you all to MSP lecture series on advanced transition metal chemistry. This is the 15th lecture in the series. In my previous lecture I did discuss about John-Taylor distortion and I was telling you about complexes of this type. Here you can see clearly 6 anionic ligands are there and copper is in +2 state. To compensate 4 charges we have lead in +2 state and 2 alkali metals in their +1 oxygen state. So, it is a charge balanced complex and this complex shows temperature dependent John-Taylor distortion. The interesting thing is with variation in the alkali metal or cation, it shows distortion at different temperatures. When M is cesium, it shows tetragonal elongation below 285 Kelvin with complex ion adopting tetragonal symmetry, whereas for M equals potassium distortion occurs at below 273 Kelvin and once again similar distortions were observed for M equals rubidium at less than 276 Kelvin and when M is thallium it appeared at less than 245 Kelvin. And above these temperatures the molecule appears octahedral due to dynamic John-Taylor effect. So, it is not only John-Taylor distortion we come across, we can also see dynamic process with temperature. So, I have listed all electronic configuration D1 to D10 to just assess what electronic configuration really shows John-Taylor distortion in complexes in case of both high spin and low spin. If you just see when we have one electron in d orbital irrespective of high spin or low spin. So, they show weak John-Taylor distortion and when we have D4 electronic configuration that means Eg has 1 electron and also in case of D9 where we have 3 electrons we come across very strong John-Taylor distortion. That is what we saw in case of chromium 2 plus and copper 2 plus octahedral complexes. In case of D5 and D3, D8 and D10 we do not see at all and in case of D6 and D7 we come across again weak John-Taylor effects and in case of low spin whether you take D1, D2, D4, D5 in all these cases we do come across weak John-Taylor distortion, whereas in case of D3, D6, D8 and D10 we do not see at all. Only in case of D7 and D9 we do come across John-Taylor distortion in case of low spin complexes. Of course, in case of D9 irrespective of whether it is low spin or high spin it is going to show strong John-Taylor distortions. Then fine, theoretically by just looking into the Eg electronic configuration to an extent T2G electronic configuration we can predict the possibility of a complex showing John-Taylor distortion. But how to assess the presence of John-Taylor distortion in complexes? Two important aspects that comes to our mind to assess this John-Taylor distortion are electronic spectroscopy and crystal structure data. Of course, crystal structure data is quite straightforward and the moment you determine X-ray structure you will come across variations in the bond length, that is bonding parameters, that should tell you whether elongation is observed or compression is observed. How electronic spectra of these complexes vary, let us look into this here. In the absence of John-Taylor distortion, absorption spectrum shows only one transition, whereas the complexes with the tetragonal distortion usually show 2 transitions and we call it as double hump pattern. How this double hump pattern appears? Okay. This is the one without Jahn-Teller distortion. You can see simple one absorption here, and when we see Jahn-Teller distortion we see two intensities here, and of course one is weaker and one is stronger. Then how to visualize this one through electronic transitions. So, let us look into the electronic transition that are responsible for showing this kind of absorption. Without Jahn-Teller distortion you can always anticipate one transition from T2G to EG, but irrespective of whether we have Z elongation or Z compression, with tetragonal distortion due to Jahn-Teller effect they show two electronic transitions, and this is the one and this is the one here in case of elongated complexes. In case of compressed complexes also we see two electronic transitions, and this explains why we see double hump pattern like this in this pattern. So, that means there is a way to assess and understand whether Jahn-Teller distortion is there or not. If it is there, to what extent it is effective, whether it is weaker or stronger can also be assessed simply by looking into the absorption spectrum of a particular complex. So, what is second order Jahn-Teller distortion? The second order Jahn-Teller distortion occurs when the excited state of the transition metal has unequal occupation of d orbitals with identical energies. That means once when you excite an electron from the ground state to excited state, and if the excited state has unequal occupation of d orbitals very similar to d4 and d9, then we can anticipate second order Jahn-Teller distortion. The ground state of the transition metal may not have unequal occupation of degenerate orbitals. So, therefore, the second order Jahn-Teller distortion is also called pseudo Jahn-Teller distortion. And if you just want to look into the potential energy surface, this is how it looks, and this is at a high symmetry point where there is no effect, and this is in case of Jahn-Teller effect, whereas in case of this one it is pseudo Jahn-Teller effect. You can see here splitting between the two electronic levels, and this is again high symmetry point, and this electronic state 2 and electronic state 1, similarly electronic state 2 here and electronic state 1 is here. So, you can also see pseudo Jahn-Teller distortion, regular Jahn-Teller distortion, and also second order effect will also be there. This is because of the excited state in which uneven filling of electron or uneven electron occupation is observed. Now, let us look into high spin and low spin complexes of the type hexa aqua M with a particular oxidation state for metals having D1 to D10 electronic configuration. So, I have listed here for 3D series starting from D1 to D10, and D1 the most common one here if you consider it is titanium 3 plus and 1 electron is there, and in case of titanium 2 plus D2 system we have 2 electrons are there, and vanadium 3 plus 3 unpaired electrons are there, and in case of D4 chromium 3 plus we have 4 unpaired electrons are there. This entire series is due to high spin complexes, and in case of D5 you have 2 levels, both are singly occupied. So, maximum unpaired electrons can be seen, example Mn2 plus. So, this is 3d5 and 4s2. When you remove 4s electrons it will be d5 system. Similarly 3d6 4s2 remove 3 electrons, so that Fe will be in plus 3 state. This is d5, and in case of d6 again Fe2 plus and cobalt 3 plus we have 4 unpaired electrons, and in case of cobalt 2 plus d7 system we have 3 unpaired electrons, and nickel 2 plus octahedral we have 2 unpaired electrons. D9 system we have 1 unpaired electron, and in case of D10 zinc, cadmium and mercury, so we do not have any unpaired electrons at all. And of course only D4, D5, D6, D7 show both high spin and low spin complexes, and the electronic configuration I have given here. This series is for low spin complexes and this series is for high spin complexes. And this is a consolidated diagram that shows various crystal field splittings of the d orbitals under the influence of different ligand field. You can clearly see here this is for tetrahedral, and of course this is degenerate system in the absence of ligand field, and when you have this octahedral ligand field, this is how the splitting is. And then if you go for D, A, B, C is this one, and if you go for D, I have listed here tetragonal elongation, and when you have tetragonal elongation, this T2G as well as EG will be further split, and this is what exactly looks like. And if you recall, this is very similar to a square planar, and of course when you have strong this ligand field, the dz square again comes below dxy, and dxy goes little bit up. So that means elongation has something to do with square planar geometry, as it shows similarities. And then the E square planar complex, you can see here, as I mentioned, it comes a little down here, and this is a typical square planar splitting, and in case of F, this is for trigonal bipyramidal one. And also you can see the relative CFSE, crystal field stabilization energy, and also relative separation between the HOMO and LUMO. In case of molecular orbital theory, we frequently use highest occupied molecular orbital and lowest unoccupied molecular orbital. The gap between that one is called crystal field stabilization energy. Same thing we use in ligand field theory also. So keep that in mind, and this is how one can show consolidated diagram for various ligand fields. So now let us look into the relationship between octahedral and square planar, which goes through tetragonal distortion and then losing one ligand to achieve square pyramidal, and eventually when you take off this ligand also in axial position, we will end up with square planar. So that means when you change from octahedral to distortion, tetragonal distortion, in particular tetragonal elongation, and then get rid of one ligand to have square pyramidal geometry, and then get rid of this one to end up with square planar geometry. Then let us look into the relative positions of various d orbitals when we try to do this transformation from octahedral to square planar. You can see here the relative energies and how they are going to transform can be clearly seen here. This is tetragonal elongation. Of course, tetragonal elongation remains more or less same for square pyramidal, there is no change. That means the crystal field splitting whatever we write for octahedral with tetragonal elongation holds good for square pyramidal geometry as well. So that means if you remember octahedral, remembering for tetragonal elongation by looking into what actually happens to these orbitals, and then that remains more or less same for square pyramidal geometry, and then here only the difference between square pyramidal and square planar is dz square comes further down, whereas dxy energy is slightly elevated, that is it. So that now remembering the crystal field splitting is rather much easier. Again I have listed here the relative energy of various d orbitals with respect to the corresponding ligand field. I have shown here, this is what exactly I wrote in the previous one, and this is written in a different format here. Okay. And here I have included square planar, trigonal bipyramidal, and square pyramidal and octahedral, and also here I have included pentagonal bipyramidal, and here square antiprism I have included, and here this is tetrahedral. So many textbooks give this kind of splitting diagram only for standard octahedral and tetragonal elongation and compression and square planar geometries, but not for many others. That is the reason I thought I should include crystal field splitting for most of the geometries we come across in coordination chemistry, with coordination number varying from 2 to 9. So now I have listed here various ligands in the order of their ligand field strength, and this we call it as spectrochemical series, and there is a background for spectrochemical series, that is crystal field theory. So crystal field theory through CFSE that can be measured using electronic spectroscopy. Later I shall elaborate more about electronic spectroscopy. So using that one you can look into the relative strengths of these ligands, and you can put them at appropriate place or give appropriate rank in the spectrochemical series. So this is in the increasing order of ligand field strength, and among them I have listed here short one. Iodide is the weakest ligand, whereas cyanide carbon monoxide and tertiary phosphines are the strongest ligands. And of course, when you look into crystal field theory through CFSC, you can judge whether a ligand is weak or strong with respect to another ligand, but why a particular ligand is a weak ligand, why a particular ligand is strong ligand, that information really does not come here. It can only show through experiment what happens, but when we go to molecular theory, I shall tell you how to classify these ligands and why a given ligand is a weak ligand or a strong ligand or of intermediate strength. That I shall clarify when I go to molecular orbital theory. So, I have given an extended spectrochemical series here. I have given an extended spectrochemical series here. This includes most of the ligands we come across, and also I have listed some important weak field ligands here, for example water, fluoride, chloride and hydroxo. And similarly I have also listed important strong field ligands, carbon monoxide, cyanide, ammonia, triphenyl phosphine. So, before I try to make it very clear about how to write crystal field splitting diagrams starting from octahedral, so let me list some of those geometries we come across among coordination compounds. The most common one is octahedral with coordination number 6, tetrahedral coordination number 4 and again square planar coordination number 4, linear we have 2 and trigonal planar 3, square pyramidal 5, trigonal bipyramidal 5, again trigonal prismatic 6, trigonal antiprismatic or octahedral same 6, hexagonal planar 6, pentagonal bipyramidal 7 and hexagonal bipyramidal 8 and cubic 8, dodecahedral 8, bicapped trigonal prismatic 8, square antiprismatic 8 and tricapped trigonal prismatic 9. We have plenty of examples for each case among coordination compounds. Now, to make you familiar with writing crystal field diagrams for any given geometry, I will start with octahedral compounds. This is what is very important. You should be able to write Cartesian coordinates and then you should be able to identify different planes we come across. For example, if you assume this is z axis and this is x axis and this is y axis, you should be able to distinguish between xy plane and xz plane and yz plane, and then you should be able to assess the orientation of different orbitals with respect to Cartesian coordinates, and also you can see their impact when the ligands are approaching the metal from different directions as per the defined geometry for that particular complex. So, first what you should do is write Cartesian coordinates, and here the origin is there. Try to place your metal at this 0 and then identify the plane, and you can see clearly xy plane and this is xz plane and this is yz plane. Now you start putting dz square orientation is in this direction. Now we know if the ligands are approaching in this direction, what would happen to the energy of dz square in that particular ligand field can be clearly visualized here. Similarly, I am going to put d x minus y square, this is along x minus x and y minus y. So, whatever the ligands approaching in this direction would have impact if electrons are already present in this orbital. Now, it is dxy is slightly spread between x and y plane. To take x minus y square and just rotate it by 45 degree, that will change to dxy. So, this is also in the xy plane, but is between the planes. Now, xz plane we have and then we have yz. So, this should be understood properly, and once you understand properly, so writing crystal field splitting diagram for anything can be very easy, and it is not memory based. You should remember it is not memory based, but you should have good analysis of impact on those things so that you can write relative energy of d orbitals with respect to any given crystal field or ligand field. Now, I have written two octahedral molecules with the 6 ligands shown here, and this is the place where metal is sitting. So, now I am putting here set of dz square and dx minus y square. You can see here they are coming on their way directly, that means energy of these two should be elevated higher, increases, and on the other hand if you see here dxy, dxz and dyz, and strictly speaking, so they are not coming on the way of ligands, but they are in between. As a result, the impact of ligand field is less on them, their energy is lowered. So, now without worrying too much, you should be able to write crystal field splitting, doubly degenerate these 2 and triply degenerate these 3. And this is how we arrived at the octahedral crystal field splitting here with respect to barycenter. It is very easy. So, remember this one, practice couple of times and you will not do any mistake in writing crystal field splitting diagram for other geometries. Now, let us look into tetrahedral molecule, and of course, you can also write like this. And to understand ligand field influence, it is very ideal to imagine this tetrahedral molecule inside a cube, something like this. This is a cube here. With intention, I have shown alternate corners with the different colored spheres. This is the tetrahedral molecule I am visualizing here. This is the metal center and these are the red ones are the 4 ligands present at alternate vertices of this symmetric cube. Now, once if you make connections to central metal from these 4 ligands, then you will end up with a regular tetrahedral geometry. And now what you should do is, the way I placed Cartesian coordinates, you place the Cartesian coordinates and then place all the 5D orbitals, and you can see the influence of ligand field on this one. In this case what happens, none of this dx square minus y square or dz square will be coming on the way of direction of approach of ligand, and in contrast dxy, dyz and dxz would be having little larger overlap with the direction of approach of the ligand. As a result, reversal of octahedral splitting takes place in this one. Hence, we write in this fashion crystal field splitting for tetrahedral molecules here. So, energy is elevated here, and if you just write, you can see they have larger overlapping, whereas here less overlapping. So, energy of E will be lower. Why we call E and T2? Because it is non-centrosymmetric. So, T2 dxy, dxz and dyz. Now, let us look into one more. This is the tetrahedral molecule just I explained. So, here one system and I have another system here. That means, here I have used alternate corners in this fashion. Let me use other alternate corners to generate one more tetrahedral molecule. What would happen if I superimpose this one on this one? Something like this. If I superimpose these two, it appears like the metal is common, but it is making bond with all 8 corners having almost coordination number 8. This is what I am referring to cubic splitting. So, that means when the ligand 8 ligands are approaching the metal to form a metal complex with composition ML8 having cubic structure, this is how you can visualize. That means if I make an attempt to write crystal field splitting for this one, it should be very similar to that of tetrahedral. That means 2 tetrahedral molecules you superimpose on another one in opposite direction, you end up with common metal and 8 ligands occupying 8 corners of cube. So, that means the crystal field splitting of cubic system is more or less is identical to that of tetrahedral. So, that means tetrahedral and cubic have the same crystal field splitting. Okay, further it is simplified. So, in my next class I shall tell you more about several other geometries. Until then, have an excellent time reading and digesting crystal field theory and especially chemistry of transition elements.